Okay, good morning. Yeah, good morning. This is Professor David J. De Los Reyes. The date for today is January 6, 2024. And I'll be having a random topic for this morning. And the title of the random topic will be AC circuit. Uh, this example problem will be most especially used for those who will be taking up electrical engineering or for those who would like to learn something about electrical engineering. Okay, let's proceed. The subject matter for this morning will be a problem on AC circuit. This is a random topic. I've done this already in the long video format, but as an additional topic, I call it random topic. Okay, it's an additional thing. So the problem will be on AC circuit. Okay, this is the problem. We are given here a circuit diagram. This is an alternating current source and connected in parallel with the alternating current source is a motor load. The total horsepower of the motor load is 10 horsepower. It could be a many motor loads in which the total horsepower will be 10. Just to simplify the indication, I will place it here. For the motor loads, it's 10 horsepower. The power factor is 85%. The power factor is lagging. And also connected in parallel with it are lights, or meaning lighting loads. Lighting loads, the total wattage of that one is 3 kilowatts. So it could be that a 30 watt light bulb maybe, okay, 100 pieces. So the total could be 3 kilowatts. Or in simple terms, the total lighting load is 3 kilowatts. The problem is just asking what will be the total current. Capital letter I with the subscript T, meaning the total current. And PF, meaning power factor. This should be overall. Meaning overall, it should be for the whole system. Meaning if we try to combine the motor load and lighting load, what will be the corresponding power factor? Okay, let's try to bring out the solution of this one. So the solution of this one will fall under AC circuit, alternating current circuit. And here, if we try to compute for the total current, we use Kirchhoff's current law here, considering this node here. Total current should be equal to I sub M plus I sub L. The total current coming from the voltage source due to this motor load and lighting load will be the sum of I sub M plus I sub L. I sub M is the motor load, motor current, and I sub L is the lighting load current. Okay, let's try to bring out the solution. Consider the motor. The formula on how to compute for the true power, okay, for AC circuit, it is given by this formula here. Capital letter P is equal to the product of EI times power factor. Actually, this one here emanates from the definition. That is, power factor is equal to P over EI. Okay? This one here emanates from this. We just computed for P. EI is actually the volt ampere, or usually you always hear that kVA. So if EI is kVA, this should be kilowatt, right? But if EI is just simply volt ampere, true power will just be simply watts. But if EI will be kVA, true power will be kilowatt. So in here, if we try to compute for current, it will be true power over E times power factor. We computed for I sub N. I now place the subscript A here. It refers to the current drawn by the motor load. And this designation here under the study of algebra, it's absolute value. I just compute the absolute value of the magnitude of the current without identifying first the so-called angle of inclination. Because supposed to be, the current drawn by this one is actually a what we call this a vector quantity. It got a real part and imaginary part. Okay, substituting values. The true power of the motor load will be 10 horsepower. Okay, we will convert that to watts. So we will multiply this by 746. So it seems we are given horsepower here, the unit, times 746 watts per horsepower. So actually this horsepower here cancel this. So there is a factor 746. This is 746. Okay. The value of the voltage is 120 and the power factor is 0.85. If we try to compute for the absolute value of the motor load current, it is 73.13 amperes. That's the magnitude. Okay. So this is 73.13 amperes. But this one here is with a certain angle minus theta. And this minus theta here is the power factor. So later on, we will be adding isoBEM plus isoBEL, which will give us the total current. It's a must that we will convert this isoBEM here in polar form first. The motor load current in terms of polar form will be the magnitude, angle. The angle will be the arc cosine of the given power factor. This is the given power factor. Okay, but I will place here a negative sign. The significance of this negative sign, this is lagging. Right? So if I will try to take the arc cosine of 0.85, that is negative 31.78 degrees. The figure is this. Hold on. I got my razor. Hold on. Oh, this is the figure, guys. This is the source voltage. It is at an angle of 0 degrees. It's always a reference vector. And the computed current, the magnitude is 73.13 degrees. And the phase angle difference is negative 31.78 degrees, the one we computed here. So this is the applied voltage. This is the current due to the motor. So this current here got two components. It got a real part and it got imaginary part. Okay, you got it? So if we try to convert this one, this current here will be something like this, right? This is isoBEM. This is the imaginary part. This is the real part. So if we try to convert this to the so-called rectangular form, we can compute for the real part. Real part will be the magnitude times the cosine. That's 62.16. This is 62.16. Okay. The imaginary part, again, trigonometry, it's the sine function. It will be the sine of this times the magnitude, and what will come out will be 30.51. We will place here a negative sign because this is downward. This is downward. Lagging power factor. The current in the motor load lags the applied voltage by an angle equivalent to the power factor. So the equivalent in rectangular form of this one will be 62.16 minus J 38.51. It got a real part, it got an imaginary part. We could not just do it algebraically, we will do it vectorially. Okay, consider the lights. Again, still, we use the formula power is equal to EI times power factor for AC circuit. Okay, and again, if we try to compute for I, it will be P, the true power, over E times power factor. The given lights, the power factor is not given, but even though it is not given, if it is a pure resistance load lights, the power factor will be 1. So if we try to compute for the absolute value of the current IL, absolute value, this is 3 kilowatts, converting it to watts times 1000 over the applied voltage 120 times 1. what will come out will be 25 amperes. And the graph of this is this. This is the applied voltage 120, and the current is in phase. That's why I place it here, it is in phase. In phase, there is no phase angle difference between the applied voltage and the current. They are in phase. So if we try to convert IL in terms of polar form, it will be the computed magnitude. Okay, the angle will be arc cosine of the power factor. This is the power factor. It is 1. And the arc cosine of 1 is actually 0. So meaning to say, the value of IL in terms of polar will be 25 angle 0 degree. 0 degree. This is IL. So meaning this is a pure real part. Right? It got no vertical component. It got which is upward. It got no vertical component which is downward. It is just a horizontal line. So if we try to convert this into rectangular, the real part will be cosine of 0, which is 1 times 25 will be 1. And the imaginary part will be sine of 0, which is 0 times 25. It is actually plus G0. So 25 angle 0 degree is actually equivalent to 25 plus G0 in terms of rectangular form. Okay? That's very critical because if we could not convert a polar to rectangular, then you will try to add, okay? If you don't know how to convert, there will be a problem. So this now falls under the study of AC circuit, changing from polar to rectangular, or rectangular to polar. It depends. If you are adding, we should be adding rectangular form. So from here, the total current now will be IM plus IL. We put this in rectangular, and so it is. So it's an AC1 already. IM in terms of rectangular is 62.16 minus G38.51. IL in terms of rectangular is actually 25 plus G0. Okay? The real part will be 62.16 plus 25. It is this. Okay? And the imaginary part is negative G30.51 plus G0. This is negative. So this is negative 38.51 and this is 87.16. And the vectorial sum of the real part and the imaginary part, okay, represents the total current. Okay, so in the computation of the magnitude, it's either that you will use a Pythagoras principle, or you take the cosine of this angle here divided by this, that represents the magnitude, or you take the sine of the angle here, divide that with the imaginary part, okay, that will still be the magnitude. Or the third one, you use Pythagoras principle. Total current will be the square of this plus the square of this, then take the square root. What will come out will be 95.29. If we try to draw the vector diagram of the voltage and current after combining the motor load and lighting load, it will be this. This is the applied voltage, and this is the total current. And the angle separating the voltage and the total current is an angle of negative 23 degrees. It is this. And this is still a power factor lagging. And one of the definition of power factor, it is the cosine of the angle between the voltage and the current. And the cosine of 23.83 degrees is actually 91 or 0.9147 times 100%. The power factor is 91.47%. It is still lagging. Okay, that's it, guys. I think this will be a good example on a problem that falls under AC circuit. Okay. For those of you who would like to subscribe to my channel or watch my channels on my YouTube channel, my channel is at youtube.com/@ProofTVJ. If you want to share it, please share. Good morning from Los Angeles.